Hello friends, welcome back to this lecture on relativistic quantum mechanics. In this lecture, we shall again deal with Klein-Gordan equation and Dirac's equation, but this time with operators approach. This method of operators is a well-established method in quantum mechanics due to its mathematical elegance. We will start with the famous equation E equal to mc square, which has cemented Einstein's legacy in the history of science. Leveraging the advantages of operators, we will extend Dirac's equation to describe moving electron and express its matrix form, revealing a set of four equations. Additionally, we will explore the wave function that represents spin of electron. You have already started watching this video and I am your instructor, Professor Shyamkant Anwane. In this lecture, we are going to write down the basic building blocks of relativistic quantum mechanics. Then we shall try and understand slope and curvature in form of derivative. Then we shall write the quantum plane wave equation. We shall understand energy and momentum operator, angular momentum operator, spin operator, and then electron wave function with spin we shall write. The traditional Klein-Gordan equation we shall derive Dirac's equation, then we shall solve it for free electron at rest, and we shall verify the commutation of Hamiltonian with LZ. Dirac's equation for moving electron, and then we shall solve the Dirac's equation for moving electron. The last point is we shall write Dirac's wave equation for free rest electron as well moving electron. The two revolutionary theories of early 20th century physics were quantum mechanics and relativity. In this video, we investigate how quantum mechanics and special relativity can be combined to give a more complete theory of electron using elegant operators. This leads us to Dirac's equation and this equation of relativistic quantum mechanics for electron. The Dirac's equation explicitly requires spin as an intrinsic property of electron. It gives improved values of hydrogen atom energy levels, including a fine structure. And this predicted the existence of antimatter before there was any reason to imagine such a thing. We only need a single equation from relativity, which is a very famous equation, E equal to mc squared. This gives intrinsic energy of a particle in terms of mass and speed of light. So here you can see E equal to mc squared. Here the mass m is relativistic mass, which depends on velocity of the object, and it can be expressed in terms of rest mass m0 or proper mass m0. So the relation that again comes from relativity as relativistic mass is equal to proper mass upon under root of 1 minus v square by c square. Now we shall rearrange this equation and square it so that we can take it into a proper form. So here finally we are at the equation mc squared is equal to p squared, that is m square v square, we are writing p squared. This m is relativistic mass, so this p is relativistic momentum square into c square plus m0 square c to the power 4. Now E equal to mc square we are using here, and we can write E square is equal to p square c square plus m0 square c to the power 4. This can be written as E equal to under root of the same quantity. However, here we are required to consider plus and minus sign, which is then going to cause us a problem in Dirac's equation. I'm telling you in advance. So this is a very important equation which we call as energy of a particle considering special theory of relativity. In short, I can call this as relativistic energy of a particle. Now, E equal to mc square, where m is equal to m0 upon under root of 1 minus v square by c square. So I'm taking this denominator upstairs and writing it to the power minus 1 by 2. And now we can expand this bracket and obtain the correction terms. And here you can see 1 by 2 mv square I have taken common. The first part is m0 c squared, that is rest energy part, constituted by rest mass, and kinetic energy 1 by 2 mv square. Inside bracket we have 1 plus correction terms which are result of Einstein's equation E equal to mc square. So the first part is rest energy, second part is classical kinetic energy, and the third section here you can see is relativistic correction. Now we have E equal to under root of Pc whole square plus m0c square squared. For a photon, the rest mass is 0. Therefore, this equation becomes E equal to Pc, where momentum by de Broglie hypothesis we can write h upon lambda, and then h times c upon lambda we can write as nu. So here E equal to h nu is a Planck's hypothesis. So here we are combining these two things, one that comes from special relativity and the second thing that is coming from quantum mechanics. The two revolutionary theories of early 20th century physics were quantum mechanics and relativity. In this video, we investigate how quantum mechanics and special relativity can be combined to give a more complete theory of electron using elegant operators. This leads us to Dirac's equation and this equation of relativistic quantum mechanics for electron. The Dirac's equation explicitly requires spin as an intrinsic property of electron. It gives improved values of hydrogen atom energy levels, including a fine structure. And this predicted the existence of antimatter before there was any reason to imagine such a thing. We only need a single equation from relativity, which is a very famous equation, E equal to mc squared. This gives intrinsic energy of a particle in terms of mass and speed of light. So here you can see E equal to mc squared. Here the mass m is relativistic mass which depends on velocity of the object, and it can be expressed in terms of rest mass m0 or proper mass m0. So the relation that again comes from relativity as relativistic mass is equal to proper mass upon under root of 1 minus v square by c square. Now we shall rearrange this equation and square it so that we can take it into a proper form. So here finally we are at the equation mc square squared is equal to p squared, that is m square v square, we are writing p squared. This m is relativistic mass. So this P is relativistic momentum square into c square plus m0 square c to the power 4. Now E equal to mc square we are using here, and we can write E square is equal to P square c square plus m0 square c to the power 4. This can be written as E equal to under root of the same quantity. However, here we are required to consider plus and minus sign, which is then going to cause us a problem in Dirac's equation. I am telling you in advance. So this is a very important equation which we call as energy of a particle considering spatial theory of relativity. In short, I can call this as relativistic energy of a particle. Now, E equal to mc square, where m is equal to m0 upon under root of 1 minus v square by c square. So I'm taking this denominator upstairs and writing it to the power minus 1 by 2. And now we can expand this bracket and obtain the correction terms. And here you can see 1 by 2 mv square I have taken common. The first part is m0 c squared, that is rest energy part, constituted by rest mass, and kinetic energy 1 by 2 mv square. Inside bracket we have 1 plus correction terms which are result of Einstein's equation E equal to mc square. So the first part is rest energy, second part is classical kinetic energy, and the third section here you can see is relativistic correction. Now we have E equal to under root of Pc whole square plus m0c square squared. For a photon, the rest mass is 0. Therefore, this equation becomes E equal to Pc, where momentum by de Broglie hypothesis we can write h upon lambda, and then h times c upon lambda we can write as nu. So here E equal to h nu is a Planck's hypothesis. So here we are combining these two things, one that comes from spatial relativity and the second thing that is coming from quantum mechanics. Here I want to highlight an important concept from calculus which we are going to use while dealing with the relativistic quantum mechanics. Let us consider that we have independent variable x designated along the horizontal axis, and on the vertical axis we have another dependent variable y, where y depends on x, and we shall call that dependence y equal to f of x. At any point on the curve, we can draw a right angle triangle. I'll show you that. So here you can observe a point here, and we can draw a tangent line. It will be parallel to x-axis. At this point again you can imagine a tangent line parallel to x-axis. Now I would designate some space point like this. Here you can see the laser pointer. So the point on the curve we are taking, and we are going to draw a tangent to that point. Now you can take slope of the tangent, very usual thing we are doing. So slope is equal to b upon a from this diagram, and we can write slope as change in y with respect to change in x, dy by dx. So that we can write as del suffix x y, rather del y with respect to x. So this is a very compact notation I'm going to use. Uh, so this represents slope. Del y x, that is derivative of y with respect to x. Then the curvature. So here you can imagine this, you can see this circle of radius r, capital R, and uh, the curvature for this curve at this point around neighborhood is 1 upon r, and this curvature can be represented as a second derivative of y with respect to x, del 2y by del x2, that I shall write as del 2y with respect to x. Fine. This we are going to explore later on. Now we are going to discuss plane wave equation in quantum mechanics. Here the wave function psi is e to the power I times kx minus omega t, where psi is a wave function that depends on position and time. I mean to say that psi is function of x and t. Psi is a function that depends on variables x as well as t. E is an exponential function. I is equal to under root of minus 1. K is a wave vector, and omega is angular frequency. So e to the power I theta, by Euler's equation we write cos of theta plus I times sine of theta. Fine. We'll be later on using this equation. The slope in time and slope in space we are going to talk about. Time slope is del psi by del t, which in compact way I can write like this, and when you differentiate with respect to time, the result is minus I omega. Why it is so? You can see this I with a minus sign multiplied by omega are the coefficient of time. So e to the power function has derivative e to the power function into derivative of the function. So I omega t, when differentiated with t, it will be I omega. So rather that minus sign is appearing here. All right. Then space slope means derivative of psi with respect to x. In compact way we can write this del psi x, that is equal to ik. How? When we differentiate psi with respect to x, e to the power function has derivative e to the power function into derivative of the function. So derivative of this exponent, it will be ikx differentiated with respect to x will give simply ik. Fine. So we are keeping this pair of equation here. Now second order derivative in time we consider, it will be minus omega square, and second order derivative in space we shall consider as minus k square. So this is the time curvature of wave function, and this is space curvature of wave function. Now mod of psi is equal to 1 everywhere. Somewhere the particle has to be there, and the probability of finding it everywhere has to be unity, that is called as normalization in quantum mechanics. So here we are going to talk in terms of operators. The energy operator is IH cross times slope. So E cap we are writing as IH cross into partial differentiation with respect to time. Now when this is operated on psi, it will give energy. Similarly, when the operator minus IH cross into slope in space, that will give you a respective momentum operator, and the space is composed of x, y, z coordinates, and when you differentiate with respect to x, multiply it with by I into h cross, This offers momentum along x direction, and this is a derivative operator which we are going to operate in conjunction with I and h cross. We are writing it in short as p hat suffix x. So p hat x is the momentum operator for x direction. P hat y is a momentum operator for y direction, and p hat z is a momentum operator along z direction. In quantum mechanics, energy and momentum operators are very common objects. They are operated on wave function psi. Here we are considering wave function psi depending on variables x coordinate of space and time coordinate. Only 2 out of 4. That is equal to amplitude A into e to the power I times kx minus omega t. When we are talking about energy operator, the energy operator is IH cross del del t operated on this wave function psi offers you energy into that wave function. Basically, this is our equation. Energy operator operated on wave function psi offers you energy into psi. So the operator that offers you energy is often called Hamiltonian operator. All right. So energy operator means Hamiltonian operator. And Hamiltonian operator for the wave function is IH cross into, uh, you call that slope in time. All right. Then minus IH cross into slope in x coordinate operated on wave function psi will offer you x component of momentum. So minus IH cross del del x is a momentum operator particularly for x component. So we can have 3 such operators, no issue. Here you must remember that here energy is h cross omega. H cross is h upon 2 pi and momentum is h cross k. So I want to mention here that I is under root of minus 1, h cross is Planck's constant upon 2 pi, and del del t is a rate of change, that is with respect to time. This is operated on quantum wave function, and when you get energy, that energy operator which E cap is no way different from the Hamiltonian. It is one and the same. Now momentum operator we will have 3 for x component, y component and z component. P hat suffix x operated on wave function psi offers x component of momentum and psi. So this is the momentum operator operated on wave function psi yields eigenvalue px, which is momentum into the wave function. Same applies for y and z component. Now two non-commuting operators we shall consider here: p cap p hat comma q hat square bracket. It is p hat q hat plus q hat p hat. This is not equal to 0, then we call they are non-commuting operators, and we cannot simultaneously measure the quantities p and q accurately in such situation, and this is uh, the gist of Heisenberg's uncertainty principle. Now let us recall angular momentum. If a particle is at location x, y, z moving with momentum px, py, pz, the components of its angular momentum are Lx, Ly, Lz. Taking the classical expression in consideration, Substituting the momentum operators, we can obtain the angular momentum operators in the same fashion. These operators do not commute, we shall see. So here we have particle m, its position is given by a position vector r bar, and it is moving along this circular trajectory you can see, and its linear momentum at this point is tangential component, and the angular momentum is along this direction, L angular momentum. So L bar is equal to R bar cross P bar according to classical mechanics. So this can be expressed in the form of a determinant. Then Lx, Ly, Lz components you can segregate out of this, and they will be as appearing on your screen. Now the x component Lx hat, x component of angular momentum, we can obtain by L hat x, and this operator is minus IH cross y into space slope in z minus z into space slope in y. So this will be x component of angular momentum. Similarly, we can have y and z component of angular momentum. Now let us look at this three pairs, Lx, Ly, Lz, Lx hat, Ly hat, Lz hat. So if you take commutation relation of Lx hat, Ly hat, it is equal to IH cross Lz hat. You can pause the video and you can verify these three equations. So here I want to conclude that these operators, these means angular momentum operators Lx, Ly, Lz, these operators do not commute. Instead, they satisfy commutation relations like this. So instead of being 0, Lx hat comma Ly hat is IH cross times Lz hat, so on and so forth. Well, in the earlier video also we were talking about spin of electron, but we haven't given a rigorous representation to spin of electron. Now we shall try to do that. We picture a particle spinning about one of the two axes such that the component of the angular momentum along z-axis is either plus h bar over 2 or minus h bar over 2. This is spin 1/2 particle for which the quantum number m sub s, m suffix s, we are talking about. So here we have spin half particle, and the quantum spin number m suffix s rolls from minus s to plus s. So it rolls from minus 1 by 2 to plus 1 by 2. Now for s is equal to 1 by 2, spin small s is equal to 1 by 2, in that case capital S will be root 3 by 2. Now here we know that the magnitude of the spin angular momentum number is square root of 3 over 2 h bar, and the component along one axis, which we usually consider to be z-axis, but not the other two components. Let's assume spin is discrete and described by the angular momentum operator s hat x. So here this is the axis of spin, and the spin angular momentum operator s hat z in Dirac notation can be represented like this. So s hat z is the spin operator s hat along z-axis for ket notation spin up particle, that is equal to h cross by 2 Ket notation spin up particle. Similarly, along the same axis, spin down particle will be minus h bar over 2 Ket notation down spin. Now here we will try to raise the Ket notation spin up by a column matrix 1 0 and spin down Ket notation as 0 1 column matrix. The superposition of two can be represented by this equation, and this is how Sz is being represented. Now we have to talk about Sx and Sy also. We will generalize that in the next slide. Here we shall try to define the product of 2 by 2 matrix having components A, B, C, D with a column matrix U, V. So the product will be A into U plus B into V will be the first element, and C into U plus D into V will be the second element. So here a proper color combination will offer you the meaningful representation. And S hat Z spin up, as I said, it is H cross by 2 Ket notation spin up particle. So this we can represent. Spin we are trying to represent by this matrix having elements A, B, C, D, and spin up Ket notation we are representing by this column matrix 1 0. Multiplication of 2, A into 1 plus B into 0 will be simply A, C into 1 plus D into 0 will be simply C, that is equal to H cross over 2 column matrix 1 0. This offers us to find out two constants A and C. Similarly, S at Z for spin down, Ket notation for down spin equal to minus H cross over 2 Ket notation for down, and then we can represent matrix A, B, C, D for spin operator S at Z. Ket notation for down spin represented by a matrix, column matrix 0 1. This yields product A into 0 plus B into B into 1 will be simply B, C into 0 plus D into 1 will be simply D, and that is compared with right hand side. This will offer you values of B and D. So in this fashion we have estimated all the components A, B, C, D, and Sz we can write completely as appearing on your screen. Now spin along Z, I want to write a generalized matrix A, B, C, D which is of the form 1 0 0 minus 1, and then we have Ket notation being represented by U, V, P, Q in terms of again a 2 by 2 matrix. The product of two 2 by 2 matrices is again a 2 by 2 matrix as appearing on your screen, and this leads us like Sz, you can find Sy and Sx. So S hat X, S hat Y, and S hat Z we have, and their commutation relation is as appearing on your screen. You can pause the video and verify the equations. So here sigma hat X, sigma hat Y, and sigma hat Z, they are said to be Pauli's matrices, and S hat Z, S hat X, S hat Y, these are the spin operators in terms of sigmas. So now we shall try to represent electron wave function with spin. Up till now, we have simply taken a spinless wave function and added a factor to represent spin up or spin down. With our matrix notation, we can now put a wave function in the spin up position or spin down position. This arbitrary state can be represented by having different wave functions psi1 and psi2 as spin up and spin down component. We call this form of a wave function a spinor. Now, this is a Ket notation psi for spin up particle, and we have wave function psi having three space coordinates x, y, z, and the fourth coordinate for time, with Ket notation for spin up particle, which is actually matrix 1 0, a column matrix 1 0. So this offers us psi xyz t 0. Fine. We have represented a particle, a wave function rather, for spin up. Now for spin down, we have psi Ket notation spin down, psi function of x, y, z, t, with Ket notation for spin down, which is actually a matrix 0, 1. This offers us a column matrix 0, psi. Now, this is spin up and spin down. Together representation offers us a bispinor psi ket equal to a column matrix psi for spin up, so appearing in red color, and psi for spin down appearing in violet color. Fine. Mod of psi1 star dv and mod of psi2 star dv represents probability of electron at some point with spin up and spin down. So bracket notation taking psi1 and psi2 equal to integration mod of psi1 square and added together with mod of psi2 square, the whole thing multiplied by dv, that we are talking about the presence of electron either in spin up state or spin down state or all space has to be 1. So somewhere electron has to exist either with spin up or with spin down, normalized to obtain this integration 1. Now the total probability that the electron is somewhere in the space with spin up or spin down is being represented by this bra psi1 ket psi2 equal to 1. Now let us try to develop the relativistic wave equation. We start with the relativistic expression for energy, substituting energy and momentum operators and applying operators on both sides to the wave function gives us an expression. Here, the Laplacian symbol is a shorthand notation for sum of spatial curvatures, that is second order derivative. This is problematic. I'll first write those equations that will lead us to Klein-Gordan equation. Here we are having E square is equal to P square C square plus M0 square C to the power 4. So in fact I am replacing M0 by simply M, and you have to just understand that this mass is proper mass or rest mass. Now employing energy and momentum operators, here we have E square and here we have P square. C is kind of constant, which is absolute constant that comes from special relativity. And when E operator is operated on itself and then operated on psi, it will look like minus h cross square second order time derivative operated on wave function, and this p square will be represented by minus h cross c whole square del square. This is Laplacian operator, which is a shorthand notation for second order curvature in space with x plus y plus z, that is operated on psi. And then we are operating this constant quantity, that is rest energy, on wave function psi. Fine. So this is what is Klein-Gordan equation is. And here we have started with E square, and the energy will have two roots, plus and minus. Moreover, the problem is that del square T gives a curvature in time. So first derivative is slope, second derivative is curvature. We have discussed in the beginning. So this is a problematic situation because it's not clear what the square root of the operator even means and how to apply it or how to solve an equation containing it. Because we have started with an expression for square of energy, the energy itself can either be positive or negative. For every positive energy solution, there will be a negative energy solution. The negative energy solution seems unphysical. The equation gives us curvature in time for the wave function, unlike Schrodinger's equation which gives us slope in time. Mathematically, to solve for future states, the system needs to specify both the wave function and slope of the wave function. So here you can see we need to know psi and first derivative of psi. This is a problematic situation and we cannot interpret mod psi square, and the value of integration mod psi square dv can change and does not remain constant. That is another problem. It's not possible to maintain the interpretation of the magnitude squared of wave function as a probability of finding the electron at some point. In fact, the sum of this overall space isn't even necessarily constant. When applied to hydrogen atom, this equation predicts incorrect energy levels, which is obviously a step down from the success of Schrodinger's equation. There is nothing in the solution of the equation that would require to predict electron spin. In fact, it turns out that Klein-Gordan equation describes behavior of spinless particles. In 1928, Paul Dirac presented a new equation of relativistic quantum mechanics that sought to overcome these problems. Very quickly we shall see this. So we are going a step down from the success of hydrogen atom explanation by Schrodinger's equation, and here spin is not included. So let's go for Dirac equation, and here instead of this equation E square equal to P square C square plus M0 square C to the power 4, we are writing as E equal to plus minus under root, same thing. Now here plus minus is appearing in an intrinsic way that Dirac has taken up for talking about matter and antimatter. He had a very strong belief in his equation and he was insisting upon the existence of antimatter because he had a belief that his equation is very accurate, employing the energy and momentum operators. IH cross partial derivative with respect to t operated on psi will give energy times psi, and momentum p is being represented by rather p square is represented by minus h cross square c square del square operated on psi, and this term remains as it is with multiplication of psi. Now here we shall prefer a system of units where h cross is equal to 1 and c is equal to 1 so that our equation looks very elegant. So energy equation, this very equation will be plus minus under root of p square plus m square. And now p square can be written as px square plus py square plus pz square. Like p bar is a momentum in general, and p bar dot p bar is this p square, and this is equal to px square plus py square plus pz square plus m square, that is rest mass. Now the Dirac's idea was, he wrote E is equal to alpha x times px plus alpha y times py plus alpha z times pz plus beta times m, so that E can be represented in tensor's form as gamma mu p mu. Here, this very form of the equation is one of the representations of Dirac's equation. Okay. He envisaged that when you square this equation, E square, this will lead to 4 terms into 4 terms, 16 terms. And the diagonal terms will be alpha x square equal to 1, alpha y square equal to 1, alpha z square equal to 1, and beta square equal to 1. So that the diagonal terms are existing to get you px square plus py square plus pz square plus m square. So this is the account of 4 terms, and remaining 12 terms should vanish, so that alpha x alpha y plus alpha y alpha x is equal to 0. That is, alpha x commutes with alpha y, alpha x commutes with alpha z commutes with beta, alpha y commutes with alpha z, alpha y commutes with beta, and alpha z commutes with beta. So if we put these restrictions, then spin automatically comes up, and the plus minus, he had a strong belief that there exists matter and antimatter. So later on the proofs came, and his equation was believed to more extent, and therefore we are discussing this even after many years. Now here I have temptation of revealing Dirac's idea in a simple version, so that you can very clearly understand that. So E square is equal to PC whole square plus M0C square squared. So this equation we are talking about, and this can be represented in Pythagorean form, where we have hypotenuse E, P on one side and M0 on another side. Here we have already considered H cross is equal to 1 and C equal to 1. Now for a photon, which is a massless particle, we have to have a consideration that the rest mass is 0. So this m0, this curly bracket, is reducing to 0, and E will be simply equal to P. So here you can imagine m0 equal to 0, that is rest mass is 0 for photon, and in that situation E square is equal to P square C square. So E is equal to simply Pc, and momentum we can write h by lambda from Planck's hypothesis, and we can write this as h times c upon lambda, which is nu, so that is E equal to h nu. So we are arriving at the Planck's hypothesis. Now here E square is equal to P square plus M0 square. Actually this C should also vanish, so that E is equal to plus minus under root of P square plus M0 square. Now Dirac's linearization we shall try for 2 terms. Let us suppose that E can be represented by alpha p plus beta m0. Now if you try to square this, it will be E square equal to alpha p plus beta m0 whole square. Now if you expand this, you have to operate one bracket on another bracket, and this leads to alpha p operated on alpha p. Here you can locate alpha p, alpha p. Then alpha p operated on beta m0, you can locate here alpha p, beta m0. Then beta m0 operated on alpha p, you can locate here. And the last term beta m0 operated on beta m0. Now here you can observe that alpha p into alpha p we can write as alpha square p square. And you can take p common and you can write alpha dot b dot alpha. I mean multiplication. P times alpha into beta plus beta into alpha, and the common m0 on right hand side we have in multiplication. Then beta square m0. So here if alpha and beta are commuting, then this middle term will be 0. And if you enforce alpha square equal to beta square equal to 1, this will lead to E square equal to P square plus M0 square. So this is called linearization proposed by Dirac. Now, which are those numbers alpha and beta? Real numbers does not offer this property. For example, 3 into 4 is 12, 4 into 3 is also 12, and if you add them, 12 plus 12, it will be 24. We want 0. So cross product in vectors can offer this. A bar vector cross B bar vector is equal to minus B bar cross A bar. But that doesn't yield very interesting situation. So Dirac proposed alphas and beta in terms of matrices. So in the units where H cross equal to 1 and C equal to 1, we have E equal to plus minus under root of P square plus M square. So here we want to write E equal to alpha dot P, so that alpha x px plus alpha y py plus alpha z pz is taken care of, and then beta m. So we are imposing the linearization and we are writing in form of operators. So here energy operator where H cross is equal to 1 and C is equal to 1, we have I, which is under root of minus 1, partial differentiation with respect to T operated on psi. This will give you energy. So this E is represented by I del T psi minus I times alpha x del x. Actually it is slope in x. So minus I times slope in x represents momentum operator. So that will be operated on psi. It will give you p psi, px psi. So alpha x px is taken care of here. Similarly alpha y py, alpha z pz, and then beta m psi, where this m is rest mass. Now E can be represented like this, wherein we have alpha x square equal to alpha y square equal to alpha z square equal to beta square equal to 1, and we have commutations like alpha x alpha y is commuting as px and py is not commuting. So here alpha x and alpha y has to obey the commutation relation. Similarly, other commutation restrictions are listed in this row, and alpha x, alpha y, alpha z cannot be numbers, and Dirac preferred them to be matrices, kind of Pauli's matrices we have seen in some earlier slide, in terms of sigma hat x, sigma hat y, and sigma hat z. Now see the problem. We have alpha x, alpha y, alpha z, and beta. We need 4 matrices, and here we have sigma x hat, sigma y hat, sigma z hat, that is only 3 matrices. So he raised the property of sigma hat x square equal to unit matrix, sigma hat y square equal to unit matrix, and so for the z case, and sigma hat x into sigma hat y is equal to minus sigma hat y. So their commutation, you have to understand that they are to be reorganized and cannot be used directly. Now the product of identity matrix with a spinner, let us suppose that UV is a spinner and 1001 is the identity matrix. So when you multiply identity matrix to a spinner, it offers spinner, no change. So like multiplying by unity. Unfortunately, we need such 4 elements alpha x, alpha y, alpha z. So we have to use these sigmas in combination so that alpha x, alpha y, alpha z and beta can be raised. So here I am rewriting sigmas and identity matrix. Then I am rewriting alpha x, not rewriting. For the first time I am writing alpha x, alpha y, alpha z, beta using sigma x, sigma y, sigma z and identity matrix respectively. Now E is equal to alpha x px plus alpha y py plus alpha z pz plus beta m. This is kind of energy equation which is kind of Dirac equation, and if you write in terms of operators it will be Hamiltonian for Dirac. We'll touch that later on. And in the compact version, alpha x px series can be written as alpha bar dot p bar, so that a dot product yields something like this plus beta m. Now in terms of operators, if I'm writing this, this becomes Dirac's equation. And now I want to substitute alpha x here, alpha y here, alpha z here and beta here. I need a 4 by 4 matrix. Why do I need 4 by 4? Here I am taking you into a Maple worksheet where we are going to run a program which is appearing on your screen. To save the time, I have already keyed in the commands. However, their execution we are doing now. I am raising alpha x matrix, then alpha y matrix, then alpha z matrix, which you can find it resembles with what we have discussed in the earlier slides. Similarly, the beta matrix, alpha x into alpha x offers us a unit matrix, alpha y into alpha y offers us unit matrix. Same is the case for alpha z and beta z. Now let us check the last command, alpha x alpha y plus alpha y alpha x. This should commute. It means that it should give you 0 result. It is offering 4 by 4 0 matrix. Now other pairs, alpha x alpha z, alpha x beta, alpha y alpha z, alpha y beta, then alpha z beta, all matrices are commuting, which are listed, and those are apparently 12 terms making 0. Thank you. So using Pauli's 3 matrices, sigma x, sigma y, sigma z, and identity matrix, we have raised alpha x, alpha y, alpha z and beta, which is in fact 4 by 4 matrix. And if we substitute alpha x, alpha y, alpha z, beta, the Dirac's equation will look like this. Now here, this 4 by 4 matrix is operated on slope of psi. And how should be a psi? Psi should be composed of four elements. So one spinor psi1 and psi2 and another spinor psi3 and psi4. So we have a bispinor psi1, psi2, psi3, psi4 being operated in a fashion that I partial derivative with respect to t operated on a bispinor psi1, psi2, psi3, psi4, which is actually psi. We have written here like this, and this is the Dirac's equation in the matrix form. So this is one more form of Dirac's equation. And if you solve these matrix, so 0 into psi1 plus 0 into psi2 plus 0 into psi3 plus 1 into psi4, this offers the order psi4, psi3, psi2, psi1. So minus I into partial differentiation with respect to x, that is slope in x, operated on psi4, psi3, psi2, psi1. Then here by multiplication we get minus psi4, psi3, minus psi2, psi1. You can identify that, and this is our final equation. Now we are in position to write Dirac's equation for electron, a free electron at rest. The general wave function psi is equal to e to the power I times px into x minus e into t. Here directly we have written momentum and energy, and then we want to substitute px equal to 0 for electron at rest, so we'll be left with e to the power minus I into et. Fine. The matrix form of Dirac's equation in the reduced version, which we have developed in the earlier slide, I have written here again, and then I'm going to raise the first equation. How it is raised? I into time in slope, sorry, slope in time, I into slope in time operated on psi1 equal to minus I into slope in x operated on psi4 plus slope in y operated on minus psi4 minus I times slope in z operated on psi3 plus m into psi1. Now here you can identify that the one I is sucked into I present in this matrix. So we have raised first equation like this, second equation you can identify in the proper color red, third one in the violet shade, psi is being represented, and this forms a set of four equations which is a Dirac equation for free electron at rest. And as the electron is at rest, the rest restriction offers that the partial derivative with respect to x, with respect to y, with respect to z is equal to 0, because the momentum is 0, so slope is 0. Therefore, the reduced equation I have written here. Then I into del T is an energy operator operated on psi1, offers m into psi1. So the first pair of equation, which is for psi1 and psi2, that is upper spinor, which is representing up spin, and the bispinor second part is representing psi3, psi4 energy operator operated offers you minus m minus m. This is a very interesting situation. E equal to mc square, this is a kind of equation that we are getting, but at the same time we are striking at E equal to minus mc square. So this was a trouble, but Dirac was so confident that his equation is showing negative energy, he attached that with antimatter, and later on his idea had an experimental evidences, so we are talking about that. Now again I am writing the same set of equations wherein we are having I into del T as energy operator operated on wave function psi1 offers plus m. Energy operator operated on psi2 offers m into psi2. So the eigenvalue is m, and it's a kind of equation E equal to mc square. And psi is psi1, psi2, psi3, psi4 composed of two spinors. So psi1, once we can write 1 0 0 0 e to the power I times same equation. Then psi2 we can write 0 1 0 0. So we are having this way the solution for equation E equal to plus m, and if we try to reinstate C, it will be E equal to mc square. Similarly, for psi3 and psi4, we have E equal to minus mc square. The big question is, what is E equal to minus mc square? Now the Dirac's equation in operator form that offers you energy into the wave function, that we shall call Hamiltonian. And the question is, does that commute with L hat z? So sigma z is 1 0 0 minus 1. Capital sigma hat z is sigma z hat 0 0 sigma z hat. This will be 1 0 0 minus 1, 1 0 0 minus 1, and this diagonal 2 by 2 is 0. Then capital sigma hat z operated on wave function psi will offer you psi1 minus psi2 psi3 minus psi4, multiplication of 4 by 4 with 1 by 4, sorry, 4 by 1. Now in units where h cross is equal to unity and c is equal to unity, capital S hat z, which is equal to 1 by 2 sigma hat z, and Hamiltonian is h hat psi equal to E psi. So the operator form of Dirac's equation we are calling h hat. This is operated on psi. The same equation I am writing, and the another equation for L hat z is equal to minus I. This h is unity, so I had it in a light shade, into x del y minus y del x. Now the question is, does this commute? So you can pause the video and try the multiplication and addition of h hat L hat z plus Lz hat h hat equal to 0. Actually, this does not commute. If it commutes, it should be 0. It does not commute. Now, after losing commutivity of h hat and L hat z, we shall try whether h hat commutes with j operator, that we define as total angular momentum. J hat z is equal to L hat z plus S hat z, and sigma hat z psi, we have already discussed this expression, and L hat z also we have discussed, that offers us this very representation. Now S hat z, which is equal to 1 by 2 sigma, capital sigma hat z, where h cross is unity, and Hamiltonian h hat, where it has Dirac's Hamiltonian. Does they commute? The answer is very interesting, that it does commute, and this leads to psi 1, psi 2, psi 3, psi 4, spin up, spin up, spin down, spin down. For energy greater than 0, energy less than 0, a bispinner. This is a very interesting situation that Dirac hunted out. For this section we are almost done, but I have a temptation of writing an equation, Dirac's equation for moving electron, where we shall consider it is having momentum only along x direction, and this is the energy and momentum operator. For x component, momentum is px, other two components are 0, and this Dirac's equation will have 4 equations, and this is a complete Dirac's equation where slope in y and slope in z will vanish because momentum is present only along x direction, and p bar is equal to px I cap, and the other slopes are 0, which are representing momentum, and therefore here we will have this additional term in the 4 equations, unlike to electron at rest where wave function was represented by psi, and psi 1 and psi 4 will have a similar kind of representation where we have some factor A appearing here for psi 4 because they have to coexist. Similarly, psi 2 and psi 3 have to coexist, so here we are having a factor B instead of 1, so that their interdependence in this set of equation is valid. The coefficient A is appearing for psi 4 component. The reason behind is the partial derivative with respect to time, which offers energy operated on psi 1, has a counterpart in psi 4 and psi 1. Similarly, psi 4 has components, remaining part in psi 1 and psi 4. So psi 1 and psi 4 are interdependent, and psi 2 and psi 3 are interdependent. So psi 1 is like this, and psi 4 is A times like this. So psi 4 is A times psi 1. Now we shall go for solution of this pair of equations. This will lead to E. The operator operated offers energy into psi 1 plus A into px psi 1 plus m into psi 1. So here A has appeared here because of psi 4. So E is equal to px A plus m. Similarly, E into A is equal to px minus ma. This leads to a pair of equation in terms of A, and we can eliminate A as px upon E plus m. So this leads to E square is equal to px square plus pm square. This restriction, the restriction on A is that this should be validated. Similarly, for psi 2 and psi 3 interdependence, we have introduced parameter B, and other two equations are not playing any role. In that situation, we can write two expressions for B, and we can eliminate B by equation px upon E plus m, and this also has to offer a binding E square is equal to px square plus m square, that Pythagorean situation. So here psi 1 and psi 2 and psi 3 will have interdependence through parameter B. So here we are in position to write the Dirac's wave equation for electron at rest and moving electron. So positive energy solution offers psi plus with spin up as a column matrix 1 0 0 a e to the power I times px into x minus et, and for spin down you can observe the column matrix 0 1 a 0, same exponential. And here the meaning of a is px upon e plus m. After substituting uh, the value of a, you can see the wave equation once again. Now E minus m upon px is equal to px upon e plus m. This offers basic mass shell equation, that is the relativistic energy equation with which we have started. So our equations are consistent. For negative energy solution, we have constant b appearing in this situation, like wave function for negative energy spin up particle, a column matrix 0 a b 0 and same exponential, and the negative energy solution for spin down, psi minus ket notation down spin, a column matrix 1 0 0 b. After substituting the value of b, you can observe here the wave function. So in general, for an electron at rest, the wave function psi appears like this, while for moving electron it has non-zero momentum, and the positive energy solution with most abundantly found spin-up electron, the wave function will appear as on your screen. So this is enough for this lecture. Thank you for your time.